All right. So next talk in the dark is by Key Martin from the Naval Research Laboratory. He's going to randomly flip a quantum bit.
Yeah, all right. That's right. Yeah, it's going around. All right. So there are a lot of points I want to make that aren't on these slides, right? And I'm going to try to hint at what they are. I don't know, I'll drop hints or whatever, but if I forget to say something that it sounds like I'm going to say, like remind me, right? So, I'm still waking up. So anyway, right, this is called how to randomly flip a quantum bit. All right, this is why it matters, right? Randomly flipping things like anything, all right, is about destroying any and all correlation that exists between two things, all right? And then the reason you want to do that is, there are a lot of reasons. So one example would be, suppose people are trying to communicate, right? And you don't want them to be able to talk to each other, right? But say it's like a QKD situation where your only option is basically to destroy it, right? Because otherwise, if you don't, they'll communicate, right? What you would do, for instance, is you would randomly flip quantum bits, right? So you might be familiar with the fact, like in QKD, that if you tried to attack QKD by measuring in a basis, right? If you just randomly chose a basis and measured, right? A lot of people think that that would destroy all correlation, right? But it's actually not true, right? What we'll see here is for instance, if you wanted to destroy QKD, what you would actually have to do is do something more like, you can't randomly choose the X or Z basis and measure. You have to first measure X and then measure Z every time. And those are different, right? That's one of the motivations. Another is so there's a subject called steganography, right? And what people do is they take information and they hide it in a picture, say, right? And then they send the picture to their friend, right, who pulls out the hidden message, right? So in the quantum context, steganography is way more involved, as you can imagine. And so one of the techniques, that people come up with to prevent it is basically going, well, somebody's passing this picture, right? I don't know if they really have something hidden in it, right? But I know most of the techniques they use, so we're going to destroy the correlation. And that's why this matters, right? It's all about preventing people from communicating in many, many ways, right? All right. And so anyway, that's what it's about. You can probably guess. I sort of, told you the point of how to actually randomly flip a quantum bit. But it turns out it's a really, really nice explanation. Right? There's a very nice way to view it, a nice mathematical way, which is really what the paper's about. Right? And like I said, there are other points that I'll make later. But so this is the slide that my talks always start off on, right? Some people are laughing because they've seen this slide a lot. There's a reason that you've seen this slide a lot, right? Because no one is fucking writing me. Right?
Nobody wants to work with you.
That's right. That's what it is. Yeah, I don't know. Do you think maybe I should put on the top free money, takers wanted? Maybe that would, this is supposed to be the art of finesse, right? I'm trying to say, I'm looking to invest in blah, right? All right, but I am. All right, so, I would like to see students funded or postdocs funded, and this part is the catch-all. That means if it doesn't fit in these three categories, and you put it here. I like domain theory. Now this is a category that I call friends. That's the friendship category. So I have these things going on right now in different ways. And a growing number of friends. And anyway, if you would like to be friends, all ideas are welcome. Send me an email.
I ask to be your friend.
It's the best way to make friends is to buy them. That's right. So anyway, that's my email. I do like domain theory, but I'm open to any idea that's interesting in any area. So I don't know how to be any clearer than that. Am I being clear? Okay. All right. Anyway, so here's an outline of my talk. I gave you a reason why we care about the interruption of communication. There are many reasons, right? All right. Then I'm going to tell you about the involution group. I love involutions. They're really, really beautiful things. It's just a function that is its own inverse, right? And actually it's like a great example of mathematical self-destruction, if you think about it. It's something that undoes itself. Now, how could you not like that? Then an extension theorem, which tells you, it's an algebra result. And then this is the point here. We're going to talk about how to factor 0. Right? If you want to interrupt communication, you have to factor 0. And then, how you would actually do this in the lab, which I've also already sort of told you. And this is not a joke, actually. The connection to JPEG compression, I'm not making this up. This is actually true. And it's really hard to believe. All right. Anyway, so let's start with this. Suppose that classically, right, people are communicating, right? And so they're sending bits with equal probability. All right. This is a good assumption to make for various reasons. One reason is this: one reason that they would send things with equal probability is that they would like to make it look like what's going on is noise, right? They would like to cover up the fact that they're communicating, right? If they send things with any probability other than equal probability, you would say, hey, wait, something's going on. This ought to be random noise, it's not, right? So it would tip you off. Maybe you couldn't read the message, but you'd be clued in, right? Another thing is this. There's a really obscure, but really, really deep result in information theory. And what it tells you is that if you have any binary channel at all, right, and you send bits with equal probability, that you get to within 94% of capacity. Doesn't matter what the channel is. That's an amazing result, right? All right. So anyway, assume that they're sending things with equal probability, right? You can prove this. This is not easy to prove, right? But I'm just giving it to you as a fact. That if you say, okay, now that these bits are coming with equal probability, I want to inject noise into the line, right, to interrupt them, okay? And you want to do it so that you achieve a certain probability of error, right? So you say, okay, I want to create this many errors. So whatever it is, all right, that's P, right? You decide up front, like what error you want to introduce, all right? Then the result is this. If that's what you want to do, right? You want to cause noise, but you want to achieve that fixed probability of error. Then the channel you use, the best one, actually is binary symmetric, right? So it means that the probabilities have to sum to 1. So some of you might call these the doubly stochastic channels in 2 dimensions, right? Some might call these the entropy increasing channels. They have a lot of names, right? It's a very interesting thing that's true. Now, why do I mention it? Right? Because classically, it means that if you want to interrupt communication, right, and you want to do it the best way you can, right, then you're going to have to be using a channel that increases entropy, right? And many, many channels don't increase entropy. All right? Like if you picture just binary channels as the unit square, because that's what they are, the binary symmetrics just run along the anti-diagonal, right? That's it. So that's a very small number of channels you have to actually use, right? So, and then out of all the entropy increasing channels, which are the binary symmetric channels, there's only one that has minimum capacity, right? And look what it is. It's randomly flipping a classical bit, right? That's what that is. See? All right. So the reason I mention this is because if we say, hey, I wonder if this could be a guide to like how to flip a quantum bit randomly, right? Then what would we be doing? We would say, well, we probably want to look at quantum channels that are entropy increasing, and then within them, look for one that minimizes the Haledo capacity. Something like that, right? All right. So if we look at the quantum case, the entropy increasing channels are the completely positive maps that take the completely mixed state to itself, right? This is I don't know if this is well known, but it's true. And those are called unital channels. Yes. Yeah. And in fact, yes. And in fact, that's true in general. A channel will increase entropy if and only if it sends the completely mixed state to itself. Yeah.
I can imagine a channel that just connects me down to the epsilon away from my data. It just comes down and doesn't move because it was. Let's say I had a channel that has a set of measures there. It takes identity to a pure state and collapses everything else down to identity. That's it. And it's a CP map. So.
No. This is absolutely true. One direction is clear, right? If it increases entropy, right, then it has to be like this. But the other one is it's not easy to prove. There's no quick.
Where can I find it?
In a paper written by someone. I don't know. I'll think about it. Yes. So the point is, but nevertheless, even if you don't buy into that, right? But it is true. It's still the case that if we're taking the classical, case as an indication of what to expect, right? Then we're still looking And, you know, here's another way to look at it. By the way, the classical result also holds. And I think really that's what you're talking about there. So you know, as an aside, the classical channels that take the uniform distribution to uniform distribution, those are also the entropy increasing channels. And that's equivalent to being doubly stochastic. And it's counterintuitive, because you tend to think, well, I mean, actually, on first glance, you might think, like, all things increase entropy, or some never do, or whatever, but it really just comes down to that one condition, having one particular fixed point. Right? So, if we look at, if we look at the unital channels, right? The one that has minimum capacity is this one, right? Convert the state of the system to be this. And its block representation is just 0, right? And so within the class of entropy increasing channels, that's what we're looking for. Okay, so this is the quantum analog of randomly flipping a qubit. And the question is, so how do you actually construct it, right? So how do you actually do this? You see, so I was talking to some friends who like do things in a lab. Like they have all this lasers and equipment and everything in it. And I was telling them, well, here's how we could, create noise. Do this, and I showed them that, but it made no sense to them, right? They didn't know how to build it. This is actually where the question came from. So now for something completely different, right? The involution group, right? Because this is how we're going to solve this problem. We are going to use classical channels, right? And actually, algebraic structure of classical channels, which is a little bit strange, but yeah. So these are the involutions, right? You have a monoid, right? So it's a set closed under multiplication with an identity, and everything is its own inverse, right? That's called an involution group. This has to be a group if it's like that, and it has to be a commutative group. And we know that the finite involution groups come in powers of 2, right? We just know this from group theory, right? Which is actually, it's actually a very nice way to justify having a state space that is a power of 2. But you'll see that comes out of this. But anyway, if we look at all the classical channels that have n inputs and n outputs, right? It turns out that you can construct the involution group within information theory, and that's the content of this result, right? One direction is obvious, right? It's just from group theory. You can only have the involution group in a power of 2, right? But the other way is not obvious, right? It's not obvious that in information theory you can not just construct the involution group. I mean, if you know enough about it, it's obvious if anything. But that you can construct it, but you can construct it nicely. See, and we actually need a nice construction, and this is the construction. So how do you construct it? So in the binary case, right, you look at 2 channels, the identity and the flip channel, right? So the flip channel is, it's the thing that takes x, y to yx, right? Okay, and that's what flip does, and the identity is the identity, and so that's Z2, right? Okay, and then what we do is for the next dimension we tensor. So so basically you think of this as 0 and 1. And you're building binary strings, right? And you end up getting the group, in all dimensions, right? And the thing we're interested in here, though, is the convex closure of this group. So once we construct it, we take its convex closure, right? And then this really has nothing to do with the talk, but I just thought it was interesting, so I put it up here because, you do need this if you want to calculate things about this monoid. But it turns out that these channels, they all diagonalize in this basis, right? Where you just keep tensoring the Hadamard operator, which is very weird. But this is very useful, when you want to calculate, because it turns out that in here you want to calculate eigenvalues, right? And it turns out that you can actually calculate all the eigenvalues. I mean, with a formula by hand, and it's actually a beautiful construction. And it comes about because you have this recursive formulation of these channels, right? And this is one of those side points, by the way. You can ask the question, how do you generalize binary symmetric channels, right? In the 2-dimensional case, a million things are possible. Maybe you say doubly stochastic, right? Or entropy increasing, or you can formulate a lot of theories about what a binary symmetric channel might be in high dimensions. This is another possibility, right? Convex sum of involutions, right? Because if you think about it here, right, the 2 involutions in the binary case are the identity and the flip map. Then you take all convex sums, and you get every binary symmetric channel. This is working in any dimension that's a power of 2. And you can see it's a natural form. But here's the thing, this group has an amazing property, right? So once we construct this group, if you take the average of all its elements, right, this is the thing you need, then what you get is the channel that I call bottom, all right? So it's the channel where every probability is 1 over 2n, right? So that's like in the binary case where the channel 1/2, 1/2, 1/2, 1/2, right? So this happens in every dimension, right? And the reason that it's important that the average of the elements in the group be bottom is because it means this theorem. So it's an extension theorem. And what it says is, suppose you had any convex monoid in the world, all right? So a convex monoid is just a monoid where you have convex sum, right? And then suppose that it contains a copy of the involution group of order 2n. So suppose it's got that in there, right? Then you can find a function, you can basically represent it with classical channels, right? Because you can find a convex homomorphism, right? From the classical channels into whatever this convex monoid is, right? And the crucial step there is that it's actually a function, right? That's what you need. You need to know that the natural mapping is actually a function. And it is, and it turns out because of property, right? So the reason this matters is if we go to the quantum case now, this is all we need to know about. Because let's look at unital cubic channels, right? And then look at their block representations, right? Now we know the spin matrices, that they're not a group, right? But if you look at conjugation by them, right? So these block representations, they are, right? And not just any group, by the way, right? A really beautiful, awesome group, right? Called the Klein 4 group, right? Which is the involution group, with 4 elements in it, right? And so here it is. It's the identity, and then these 3. This is the same as Z2 cross Z2, okay? Right? And so right there, what do we have? We have a convex monoid, right? That you get by taking block representations, eventually increasing channels, right? And then we have a convex linear homomorphism from the convex closure of the Klein 4 group, into there. And so what can you do with this thing, right? So this is the weird part. Like, you can basically solve the problem just doing simple algebra and absolutely no quantum mechanics of any kind. So here's how you factor 0, right? You take this convex linear homomorphism, whatever it is, right? And you know that it maps in. You know that it maps, that it gives you the Pauli spin, they're not spin matrices, but they're the representations, right? So whatever the classical channel is that goes to spin x, you call it x. And the one that goes to y, you call it, y and z. And then the first thing that happens, right, is if you apply this thing to bottom, right, so that's the channel where all probabilities are the same, right, then you have to get the 0 matrix. And it's mostly because bottom is an algebraic 0. Right? So we know bottom is an algebraic 0 in classical channels. So then it's got to be an algebraic 0 in the image. There is just one technical thing you need to know a little bit more, but that's basically why. So bottom always has to go to 0 if you have this homomorphism, right? Then the next thing is, remember what I said? If you take the average of all the elements in this group, no matter what dimension you're in, it always adds up to nothing, basically, right? So then because of that, when you apply the homomorphism, right, remember it's convex linear, right? You get this, which we also know is true, right? If you randomly choose between the spin operators, you can destroy all correlation, right? But the interesting part is that this is a consequence of just classical reason about classical channels. And so then here's the step that I like the most, right? If you take the Klein 4 group, right? It doesn't matter what you call these things. Z always has to be xy, right? And then, so because of that, it means that you can factor this as this. You see? Right? And because you can factor this way, now you apply the homomorphism again, and it preserves products, right? As well as convex, sums, right? And so it gives you this, right here. You see that? And that's a factorization of 0, right? So at this point, most of you know what this is, but just in case not, because it can actually be a real pain in the ass to show this. But these 2 channels right here, right? Randomly choosing between spin x and the identity, and over here, their product is 0, and they are the block representations of measurements in these 2 bases, right? So the interesting thing, right, is 2 things. First, you can factor 0 just by working with classical channels, right? And then when you do, you get a meaningful factorization. At that point, you do actually have to do a little bit of quantum mechanics, to figure out right, what you're talking about, right? But up until that point, you actually don't. And so this is a factorization of 0, and it means something. And it's something very clear, right? It means, what do we do to destroy autocorrelation? We measure in one basis, and then we measure in the basis orthogonal, right? And this is like, this is what Ross was talking about when he talked about mutually unbiased bases. That's literally, to me, that's what it is. It's the way you destroy communication and correlation, right?
You don't need a full mutually unbiased basis. You just need two.
Yes, right.
Biased.
Right. No, but I'm saying this is an example of something you can do of things that you talked about. That's all. So now, see, here's the thing. This is an interesting equation, and so I spend a lot of time at at different labs where they've built like QKD systems and stuff like that, and I find that it's a weird thing people do, and this is a point to really stress to people, like in quantum cryptography. So what it is, it's like not everybody seems to appreciate the problem of randomness, right? I mean, quantum cryptography is not secure at all if you don't have real randomness, right? And most of the time when people describe quantum crypto, they start off by saying, well, okay, generate some random bits at random, pick a basis at random, and then they talk about pass it and measure in a basis. But the point is, in quantum cryptography, every step should be a measurement. Literally. That's the only way it would be really random. And if it's not, if you're using like a pseudo-random number generator, you can actually simulate the whole thing. And the weird thing is, I'm not going to say what place, but it's a very famous place, and it's built like a very, very practical, I mean, it's a really good system. And I was talking to them about it one day, and in their circuit board for QKD, right, they actually have a pseudo-random number generator. I went, wow, do you realize what you've done? And they said, oh, that's okay, because nobody's going to figure out it's too difficult. and I said, well, but that sort of defeats the whole point of quantum cryptography, doesn't it? You know what I mean? That's why we had it to begin with. Anyway, the reason I mention this, right, is because you see this equation right here. I mean, it's true mathematically, right? But the point is, operationally, they're very different things. You see? See, this one right here says we have to figure out a way to randomly choose between these spin matrices, right? And over here, this one says we don't have to generate randomness at all. We can leave it to nature, right? And so another way to say what I was just saying is that you want to do this. That's how you want to get randomness. You don't want to leave it to like some engineer to come up with some stupid coin flipping thing that doesn't work, right? This is what you want to do. Or another way to look at it is it tells you if you want to build something random, here's how to build it, you see? And so there's this wonderful coincidence between here's how you do something that's really random. And why does this hold, right? It holds because we have the involution group in dimension 4. It's because it's the Klein 4 group. That's why. That's all it is, right? But it's this great connection between randomness and the Klein 4 group. Anyway, I like it, because like I said, I like involutions. So then, I want to tell you this, and this is like, I'm not making this up. I have a friend, he's a very weird guy, and he studies things that are like very practical, right? And he's into steganography. He's a very interesting guy, though. And he asks very strange questions, and he performs really weird experiments, okay? So I'm just going to sort of paraphrase what he did. Basically, JPEG compression is something that takes a picture that's pure, and then you compress it, right, to make it smaller and all, right? Anyway, when you do this, the picture's broken up into like blocks of bits, and the bits change under this transformation, right? So what he did is he went, okay, I'm going to look at every block, and I'm going to look at the least 2 significant bits, right? So you have a binary string of length 2, right? And he said, I'm going to see how those bits change when you apply JPEG compression, right? So what you get is a channel with 4 inputs and 4 outputs, right? Then he ran a whole bunch of cases, and he calculated some probabilities, right? And when he did this, it turned out that he got a matrix of this form. All right? I mean, like all the time. Just trust me, it's true. I mean, if we wanted to prove this, it'd be really hard. You have to talk to people who wrote the software and see like why or whatever. But this is always true, right? This form comes up time and time again. And okay, well, this form, that's what we were just talking about. These are the convex sums of the Klein 4 group. That's what they end up looking like when you just write them out, right? They end up looking just like that. So what's weird is basically every time you compress a picture, you're actually generating this matrix, and that matrix is in one-to-one correspondence, right, with a convex sum of spin channels. So it's literally simulating A spin, I mean, it's weird, but it's true. You know, it's a wide, I don't have any idea, you know, but I just thought it was interesting, and I guess the point I'm trying to make is that this class of channels, I've tried to make the case that they're natural, okay, and they have all these, like, beautiful properties, but they also arise just, like, in completely other contexts, right, and this is sort of one of the things that lets you know, oh, wait a minute, this is a natural class of channels, right. The other thing about them is, you know, you can ask the question, how do you generalize the notion of a binary symmetric channel, right? Well, part of the generalization, and this is why people really like them, it's easy to calculate stuff, right? It's easy to calculate the capacity. Everything is nice about them. You don't have to try, right? Now, if you say, well, all right, double stochasticity is the way to extend it, it's not easy anymore. It's not, try it sometime. take a random, you know, doubly stochastic channel and try to calculate its capacity. You probably can't. You know, I mean, that ought to be a theorem somewhere. Somebody should prove that. It's difficult, right? But in this particular case, if it's a convex sum of involutions, it's really easy. I mean, because I can tell you right now, the capacity of this thing is log 4 minus the entropy of one of the rows. See? Log 4 minus the effect of the noise. That's it. But, you know, and that's true in every dimension. So that's, you know, and the whole theory is fairly easy. And the other weird thing is you can actually, if I show you this matrix and I say calculate its eigenvalues, right? When you write it like this, it looks really difficult, right? But like I said before, you can actually show that this thing is diagonal. You know, like I said, in H tensor H, right? In that basis, it's diagonal. And so you can calculate its eigenvalues perfectly. And they turn out to be like 1, you know, and then like sums of x1 through x4 where you have minus signs alternating, right? It's just a beautiful result. And so, what do I think we learned? Well, so the representation of like practical qubit channels with classical channels, you know, how to randomly flip a quantum bit, but the approach is that we just do basic algebra in a model, and then maybe this is the thing I like the most, that it's a new class of naturally occurring channels, you know, and the way you summarize them is just they're the convex sums of involutions. Okay, so that's it.
Any questions or remarks?
Refill, right here.
Oh, no. I have to take a break for at least a couple hours. I'll come to you at lunch, maybe.
So if you have to, so I guess there's a bunch of interesting questions, but so let's say I had a cube trip and you had to do this. Do I need to do, I mean, so you don't get the same mathematical structure, but you still have like a Pauli, like you have a generalized Pauli group. So what you have there, like, as a point of information, the person said, oh, you know, you apply a Pauli channel.
Right.
There is a Pauli channel on the cube trip. So that, you know, and I could just say choose one of those at random. That would be one. I think that would randomize.
Right.
Properly. Now, does that have the...
Right, but can you do the
can that be
factorization?
turned into...
Right, I only know in a power of 2. I don't know.
In a power.
I don't know, but actually that's one of the, I said I left out many questions, that's one of them. Like, I think it's a really interesting question. It's like can you, because you know the importance of the factorization is that randomness gets forced to nature.
You believe nature is random, but...
Yeah. No, I never said I believe anything about
I mean, nature could be deterministic, so maybe it's better to make a random choice in your head.
But okay, I guess this is how I'd say it. I want to achieve the effect of randomly choosing between spin channels, but I want to do it with steps that I understand concretely. You know what I mean? Like, I really understand, because I've been in a lab many times, I've seen, okay, you measure this way and then you do it this way. So I get that.
So are you happy? So I'm actually unhappy with when they do say that a Bell version of key distribution, if they use a photon and a beam. So one way of making the random basis choice, they take a Bell pool. And there's two things they can do. One is they can use a random number generator to switch things, and the other they can do is they take a separate photon, put it on a beam splitter, and make the random choice of bases that they measure. Are you happier with that as a way of making a random choice?
I like to use quantum mechanics to do all the randoms. Every choice, literally. You know?
I'm not 100% I mean, just at a pragmatic level,
Right,
I
no,
think
no,
the
yeah.
eavesdropper is more likely to be able to know something about the physics of my beam splitters and photon sources and no biases and that kind
Oh,
of
no,
thing.
but you know,
Then some, like, I'd prefer to have my security based on mathematical theorems if I could. Now, there's good computer science reasons to believe that we can really generate damn good random numbers. I'm much happier with that than with something like, photons on a beam splitter being random.
right, no, but the problem is that if you use some method to generate a random number and the eavesdropper knows the method you're using, and the way we do things in security is we say, okay, whatever we know, they know. Why? Because spies steal secrets. That's why. So if we're using a mathematical approach, basically they have it. They can steal it, and then they can simulate it. And that's why I favor.
Well, no, in this case, they know the generator, but they don't know the seed to the generator.
Right,
So,
and this
it's exactly the same. You've got a random string. I know my random seed, and that's what we keep secret.
Right, no, but that's what I'm saying. You can't always do it. They steal those things.
But why is quantum physics more random than?
That's a really great question. And I didn't say it is. But this is a great way. Why is it more random than right? That's a really good. This is one of the things that I'm always trying to get people to think about and talk about. I don't know.
I think actually you could take a classical object, like a classical wave packet, and measure it in 2 different bases and still get the same result, right? You still get some. I mean, I don't know. I mean, it's really cool, but
yeah.
I mean, you could make a classical,
Yeah,
object
that's
behave
basically,
exactly like
like,
that.
I think a better way for me to say this is that's the question that I'd like to know the answer to, actually. The randomness we can generate with measurement, is it better than the randomness we can get someplace else? But like I said, if any kind of approach to randomness based on a seed or anything, they steal stuff like that. I mean, they just do.
I suppose one could say that even if the eavesdropper knows everything about your system and you're using the photon that goes through the beam splitter with 1/2 probability it gets reflected or transmitted, there's no way they can predict what's going to happen.
That's your philosophical belief about quantum mechanics. What I was saying is yes, it is. If you're a Bohmian, you say, of course they can predict it. If I'm going to give the eavesdropper arbitrary physical power, she might know the quantum trajectories of the photons, and she will know where it's going.
No.
So,
Yes.
If you throw a quarter in the air, there's no way to predict it, right?
In Bohmian
Across the
mechanics,
room.
it's just a lack of knowledge of the trajectories, but there's no physical restrictions.
Randomly stop this.
You understand? Like this.
So obviously, Key
It's
is
a philosophical difference.
inspired an interesting discussion here, which we should continue for the lunch and drinks. But let's thank you again.